Okay, so we're picking up in Chapter 16, Section 1. In the last class, we did a bunch of calculations of solubilities of compounds. And so now that we've done those calculations for solubilities, we've looked both at molar solubility and solubility from the standpoint of what's most commonly presented in literature, which is the mass of substance that dissolves per 100 milliliters. When we look at solubilities, we can't necessarily compare the solubility of a substance directly from the KSP values like we could with an acid and its Ka value. At least not in all cases. In some cases we can. And so in the cases that we can, those cases are going to be when we have a salt, or when we're comparing two salts, right, that dissolve and dissociate to produce the same number of ions. And that's a key here, right? If they produce the same number of ions, we can compare them directly by KSP values. And so keep in mind, right? When you have a KSP value of something that, say, dissociates into two components, right? So you have, say, a metal and some sort of a non-metal, and that dissociates to give you, metal plus, X minus, both aqueous. And if you're comparing things that just give you 2 ions, you can compare those directly. But you can't, for example, compare something that is an MX formula to something that is an MX2 formula. And we'll start to see sort of why that is just with this slide, right? Because this is not the same thing. And you can think about it from the standpoint of how those KSP values are calculated. Okay, so if you're comparing the first one, you'd get a KSP that is going to equal the concentration of the metal times the concentration of the nonmetal, right? But if you compare it to the second KSP, right, in that case, you have the concentration of the metal, let's say +2, if I'm doing this right, or reasonably. So the concentration of the metal times the concentration of the nonmetal squared, right? And so in that case, you're actually getting you have a very significant difference, because these are really small values. When you square small values, you get a very different number than when you cube small values. And so that's a key difference here. So if you were to compare something like silver iodide to copper iodide, to even something like copper sulfate, you could compare these solubilities just based on the KSP values, because they dissociate into 2 ions. So you know that they're going to be, those KSP values are reasonable measures of the relative solubilities of those 3 compounds. So the most soluble would be the calcium sulfate. The least soluble would be the silver iodide, right? The smallest KSP, okay? So that's a key for us with our comparisons. But if they dissociate to give you a different number of ions, well, in that case, you actually have to go and look at not the KSP values, because yeah, you can get some information about these KSP values, but it doesn't give you direct comparisons. And so you notice these are really, really small numbers: 10 to the minus 45, 10 to the minus 49, 10 to the minus 73. But if you look at what they dissociate into, right? Copper 2+ and sulfur 2-, right? I guess I could put those down, if you will, right? Or on the next one, right? It's 2 silver ions plus 1 sulfur. Even though the anion is the same anion for all 3 of these substances. So here you get 2 bismuth. Right? So even though you get you have sulfur in each of these cases, right? Your KSPs aren't going to be comparable because of the number of particles that it dissociates into. Now, if you go and actually do the math on these, and I'll leave it to you to do the math to compare these, but the math is somewhat complicated, and especially when you get to the bismuth, but you could potentially do a fifth root, if you will, for your ice boxes, but you would actually get molar solubilities that are listed here. And so even though the KSP value for the bismuth is the smallest by far, right? 10 to the minus 73 as opposed to 10 to the minus 49 or 10 to the minus 45, right? Even though its KSP value is the smallest by a lot, you'll notice it has the biggest molar solubility. And so when it comes to the comparisons of solubilities of different substances, you have to compare the actual molar solubility or the grams per 100 milliliters if you're really going to do it right. And that works well if you have the same number of ions, or rather two substances dissociate into the same number of ions, but it doesn't work well when those substances dissociate into different numbers of ions, okay? So that's a key thing to note here. The direct versus not so direct comparisons of solubility based on KSP values. Okay. So another aspect of solubility and solubility chemistry is the comparison of reaction quotient Q. So Q is same idea that we've done in the past, right? In this case, it's QSP. So when we've done Q in the past, right, it was always a Q versus K, right? So Q and K, well, those were equilibrium constants and reaction quotients. Well, the reaction quotient for a solubility equilibrium is called the ion product. Okay, so it's not the ion product constant, which is the KSP, but it's just the ion product. So here, that Q, right, the QSP for a given substance, so this is metal and non-metal that dissociate. Well, you'll get, as you know, the stoichiometric coefficient for the metal will be whatever its subscript is over here in the compound, and it's going to have some sort of a charge to it, right? The stoichiometric coefficient on the non-metal will be the same as the subscript over there on the solid, and you'll get the charges that balance out. Just as sort of just a generic equation for the solubility of a substance. And in this case, you're looking at it from the standpoint of the QSP, right, where the P and Q, again, are the stoichiometric coefficients respectively. So this is just equilibrium chemistry that we've seen in the past. We just happen to give it this subscript, SP, for the solubility product. So if you're looking at something like, magnesium carbonate, solid, right? In that case, since we know magnesium carbonate dissociates into a magnesium 2+ plus a carbonate, well, it's going to have a QSP, right, that has the same basic structure of the KSP, similar to what we've done with Qs and Ks in the past, right? So concentration of the magnesium ion times the concentration of the carbonate, right? And so in that case, it's just not equal to a constant. This can be under any sets of concentrations, but you can compare it to a constant like we've done in the past, right? So at saturation, QSP is equal to KSP. So let's look at some of those relationships and just talk about it from the QSP and KSP standpoint. Okay. If you know, so you're going to calculate these concentrations. How might you do that? Well, you might say, oh, we add two solutions together, sort of like we did in chapter 4 in Chem 101, where we had silver nitrate and sodium chloride. When we add those two things together, we can calculate that QSP value. If we compare that to the KSP, and the QSP is larger, right? Remember, if Q is bigger than K, right, it says that the reaction is going to go from right to left, right? Well, if you have something, here an example being that silver chloride, because remember, always our solubility equilibria, that should be a solid. Our solubility equilibria are always written such that the solid is on the left and the ions are on the right. Right? So if Q is bigger than K, it pushes the reaction backwards to make more of the solid. So in other words, that's where you have a precipitate. If you have QSP is equal to KSP, this says that it's a saturated solution. And so you don't have any precipitate in this reaction. You won't have any solid in the bottom of the container because it's a saturated solution. And so that's a very specific case for a solubility equilibrium, is when QSP equals KSP, there's no precipitate, but you are at that equilibrium point. Okay. Now, in the other situation, if QSP is calculated to be less than KSP, well, if we think about that silver chloride reaction, right, where it dissociates, well, in that case, right, this says, well, if QSP is smaller than KSP, this reaction is going to proceed from left to right. And so if that's the case, all of the salt dissolves, okay? And so there's sort of a difference here. We can say, oh, all of the salt dissolves. So what does that mean for this reaction? What it really comes down to is that no precipitate will form. So there are two situations where you're not going to get a precipitate. It's either when you have a saturated solution, or if your QSP is less than KSP, the reaction would proceed from left to right. But really, what you see in this reaction, because if you think about it, right, we're taking two solutions that are soluble, we mix them together, you don't see a precipitate, so you don't observe anything under those conditions, right? So if no precipitate forms, yeah, the reaction may be at equilibrium, right? Or it could be that the reaction proceeds from from left to right. You just don't see a precipitate because you don't ever reach that point of saturation in that particular reaction. So no precipitate would form there. And so we can use that to determine whether we're going to get a precipitate or not if we add common ion to a solution. So again, common ion is the common ion effect is something we talked a little bit about in when it came to buffer chemistry, but we can also use it when we think about the solubility chemistry. So if we have a solution of calcium carbonate, right, or we're going to make a solution that has calcium carbonate in it, we can determine how much calcium carbonate can dissolve, or at what point we might see a precipitate. So since the calcium carbonate dissociates into calcium 2+ and carbonate, CO3 2-, and we know the KSP for that, right, as it's seen here. Well, if we wind up adding some common ion, in this case, we can add sodium carbonate from a solution of an aqueous solution of sodium carbonate. So sodium carbonate is soluble in water. And so if we add 100 milliliters of 1 molar sodium carbonate to a solution of calcium carbonate that's below the saturation point, in this case, 0.250 times 10 to the -5 molar. Well, what we can do here is actually look at the amount of each of these different components, knowing that the sodium ion doesn't really have an effect on the overall solubility. But since our KSP expression is, right, calcium 2+ concentration times the carbonate concentration, right, adding that carbonate in the form of sodium carbonate can have an effect on whether or not we'll get a precipitate. And so the way we have to do this is really figure out, well, when we add the sodium carbonate, the calcium is affected, the concentration of the calcium is affected only by the dilution, because there is no calcium in sodium carbonate. But the carbonate's concentration is affected by both the original amount of carbonate that we started with and the amount of carbonate that we add. So a good way to set this up is actually to set up an icebox, okay? And so that's what we'll do here. So we've got our calcium carbonate. Try this again. Arrow with water reacts to form calcium 2 plus carbonate, CO3 2 minus. And so we'll set up the icebox like so, similar to what we've done in the past. Okay. Again, with the solid calcium carbonate, we don't have to include that in the icebox because it's not part of our equilibrium constant expression. But what we do have here now is we have an initial concentration. And so what we have to do in here, we have to put in there the concentration after we add, in this case, the sodium carbonate. Right? So essentially what we're doing here is a dilution of the original solution. Okay? And so for that, it's actually pretty straightforward, right? We have an initial volume of the calcium carbonate, an initial concentration for the calcium carbonate, but we also have this added volume over here, right? We have this 100 milliliters that we're going to add. Now, if we don't take into account the added carbonate yet, we can take that into account in the change. So if we do that, what we can do is say, well, if we have essentially an M1 V1 equals M2 V2 calculation, well, once we do the dilution, we can say, well, our M1 is 0.250 times 10 to the minus 5 molar. Our V1 is 1.000 liters, is equal to M2, which is what we're calculating here, and V2, which is 0.100 liters. Okay, so we do that dilution, we wind up getting a new concentration of both the calcium and the carbonate of 2.73 times 10 to the minus 5 molar. That's not right. 2.273. I lost a 2 looking down at my paper. 2.273 times 10 to the minus 5 molar. Can't have a higher concentration after a dilution. So those are both going to be 2.273 times 10 to the minus 5 molar. Okay. And then our change, well, as we add this calcium, as we add the sodium carbonate, we're not adding any calcium, but we are adding some carbonate. And so the amount of carbonate that we're adding there is, again, a dilution. And so, again, we're going to do M1 V1 equals M2 V2, but now our initial concentration is the 1 molar, and our initial volume is the 100 milliliters, and our final volume is still that added, oh shoot, and that's what I did wrong over here. Excuse me. Let me go change something in here real quick. This should do, come on, nope. Stop that. This is not letting me do what I want to do. There we go, now it is. There we go. That should be 1.1 liters because it's the added volumes, right? That's the 1 liter plus 0.1 liters. Right. So here, if we do our M1 V1 equals M2 V2, we've got our 1.00 molar times 0.100 liters is equal to M2 times 1.100 liters. And so we divide it all by 1.100 liters. We get M2 is equal to 9 0.091 times 10 to the -2 molar. And so what we can do is see that, well, we add in a concentration of 9.091 times 10 to the -2 molar carbonate when we add in this 100 milliliters of 1 molar sodium carbonate. And so at equilibrium, we have 2.273 times 10 to the -5 molar and of the calcium, and excuse me, that's not right. Try this again. Should be 9.093, right, 273 times 10 to the -2. Here, I'm going to erase some of those. I don't need all those significant digits in there. Get rid of them and make it a little clearer. Okay. And so to do this calculation, all we have to do now is say, okay, well, our QSP will equal 2.273 times 10 to the -5. Okay. Times 9.0932 times 10 to the -2. Okay, and so the QSP comes out to be 2.2067. 2.2067 times 10 to the -6. And so now you can compare those two, right? You can say, okay, well, 2.2067 times 10 to the -6, that's our QSP. And our KSP is 3.3 times 10 to the -9. And so in that case, QSP is much greater than KSP, right? And so if we go back up to this chart, right, we can see, well, if QSP is greater than KSP, we'll have a precipitate. So yeah, a precipitate forms. Okay. And so that's how one of those types of calculations would work. So you can do this for any type of added common ion to see if there's going to be a precipitate. So essentially now you can quantitatively determine how much precipitate you would expect for reactions that you did back in Chem 101 in Chapter 4 when you were doing precipitation reactions. Okay. And then one last thing for this particular section is when that common ion is involved in an acid-base reaction, you have to think about how that would how that could affect the solubility. So, and this is really just based. So this is pH, the effect of pH on solubility. This is really just applying Le Chatelier's principle to this chemical reaction. So, if you're looking at the solubility of something like calcium carbonate, right, it dissociates into calcium and carbonate. And the carbonate, remember, that is the conjugate base of a weak acid, right? So that's a weak base. So if you add an acid to this, right? If you add an acid, you're adding H+, it forms bicarbonate. Oop, that should be -1. Right, so it forms the bicarbonate ion. And so when you think about it, yeah, that reaction here, if you add a strong acid to this, it is pulling that reaction down toward the bicarbonate, which means you're removing carbonate from this equilibrium, right? And if you're removing that from the equilibrium, then that causes this reaction based on Le Chatelier's principle to pull over to the right. So it means that calcium carbonate will be more soluble in an acidic solution, right? And we'll explore this, or at least something similar to this reaction, a little bit more tomorrow when we dive into complex ion formation from just a minor standpoint. We'll see something similar reaction to this, where you have multiple reactions at play that can have an effect on the overall solubility of something. So we'll see that a little bit more tomorrow. And so with that, we're going to keep our lecture time short today, and we'll go on into the lab. Any questions on the material before we head on into the lab? All right. What we'll do is we'll stop this recording.